My name is Ankit Rohatgi. I'm a senior software developer at ANSYS, and I have a PhD in chemical engineering from the University of Notre Dame. Those of you who've heard of ANSYS probably guessed that I work with a lot of structural analysis and fluid dynamic simulations. But what I'm here to talk about has very little to do with my work at ANSYS or what I did at for my graduate work. This is, in fact, an interesting side project that I've had for a while. And this is something that started with maybe 100 lines of code that I had in graduate school, and something I just started sharing out with my friends and colleagues. And it slowly, over time, grew into a very useful product. And I think a lot of you would actually end up using it at some point in your work. Before I go further, I'm curious, how many of you have actually checked out the website or even used this tool at some point? OK. So my next question is, how many of you have run into a situation where you have a static image of a visualization, but you have no raw data to go with it? So this tool is basically meant for you. And for those of you who have never run into this situation, this actually happens quite often. For example, you're maybe reviewing a journal article, and you want to validate somebody's claims that they've made this fancy plot, and you want to check those numbers. You could be a hobby electronics engineer, like sometimes I like to build some circuits, and you're going through these data sheets full of characteristic curves with IV charts and whatnot. Or you could be a chemical engineer, and you just bought this fancy pump, and you want to do simulations in your plant. And the only thing the pump provider has provided you is maybe some pump curves, which are just images, and no raw data, really. So in those cases, how do you proceed? Like, what is the first thing that you would do? Of course, many of us would try to email the author and say, hey, where's the data behind what you plotted? I want to play with it. And in many cases, you may hear back, or you just might not hear back anything at all for months. But in many cases, like, for example, the charts on the right, there might not be anybody you can email. For example, this is a 200-plus-year-old, or about 200-year-old chart from William Playfair. And there's really no one you can contact and try to get the data. So what do you do if you're not familiar with any of the tools? The most intuitive thing that you would do is try to take the image file and drop it into your favorite image editor, like Paintbrush or GIMP in this example. And you would say, hey, I know a bit of math. I can do linear interpolation. And I can start counting these pixels and figure out at which pixel which data point is. But that's a super painful way of working. Nobody wants to work like that. I've actually seen some people print out charts and use rulers and pencils and try to extract data out of those things. Again, not a recommended way to go. But a lot of you would say that this problem is not new. It's been around since charts have been around, really. And so why haven't people written tools that I could just go and download and start using? And when I was a graduate student, I did exactly that. I started going and started trying one after the other, every tool after another. And I very quickly realized that there are a lot of issues with all the existing tools that are out there. The primary thing is, if you're a Linux user or a Mac user like me, you're usually out of luck. And a lot of these tools, since it is an old problem, a lot of them tend to be not maintained anymore. They might be written by somebody who is completely retired. A lot of these tools also supported only XY charts. So if you have a crazy polar diagram or a ternary diagram, you're back to using your Paintbrush and GIMP. And a lot of these tools also had very complicated user interfaces that made life very difficult. And I found myself making a lot of mistakes. There's some even expensive tools. They're like $300, $400 tools for a poor graduate student like me. That was still not a feasible option. They did not seem to be any bit better than anything else that was out there. And of course, there was a problem of not having it to being super automated. So I was still spending a lot of time trying to extract data like this. The ultimate goal for things like this, of course, is to have a completely automated approach. And over the last few years, many people have called me and asked that, why is there no tool that I can just upload my picture and I just get my data back? Because the thing is, OCR tools, for example, for tables or text, they've been around for decades. But something like this, there is really nothing automated. So the main problem is that you need a very high degree of accuracy that you don't need with just analyzing text. In this case, you want to pinpoint your axis coordinates. You want to be very precise in where your data points are located. And in many charts, you also want to understand what the intent of the user is. You want, in many cases, somebody operating these tools would want to extract data only at a certain point and for certain data curves, which is very hard for an automated approach to kind of figure out. I have some citations all the way at the end of this. If you're really interested in this topic, there are about 4 research groups who've tried attempting this, and they've had some mixed level of success. But still, there's nothing that you can just drop your pictures in. So when I was a graduate student, I was doing a lot of fluid mechanics experiments. And I was going through a lot of videos of particle tracking, velocimetry type stuff. And I was writing tons of MATLAB code, teaching myself image processing, and trying to figure out how to deal with all this. And I was also getting interested in a lot of web-based programming. So I thought, hey, can I write a simple piece of code that I just load a picture in an HTML5 canvas and start doing some basic image processing and just extract, what I can. So I wrote these 100 lines of code, and soon my roommate asked for it, and then he passed it on to others, and others passed to further others, and soon I knew within a few months there were strangers on the internet telling me what they need out of this tool. So with that, I would like to do a very live demonstration. We haven't had as many choppy live demonstrations today, so I'm going to try to do that. So if you go to the website, all you really have to do is go to this green button on the right, which says Launch App. There is no need to log in. It basically loads almost instantly. And I'm going to take the chart that I showed a few slides ago by William Playfair. So this is the same 200-year-old chart that I showed earlier. The first thing the tool would ask you is what type of chart it is. Of course, something like this could be automated in the future, but right now it asks for some manual input whenever image processing is hard. So in this case, I would pick to align the axis. So in this case, the tool wants me to specify what the coordinates are on the axes. So I'm going to go and just pick 2 points on the x-axis, 1770, 1830. You can use your keyboard cursor and make really fine adjustments. You can also kind of zoom in and out as you please. So I need 2 more points on the y-axis. And 120. So what this is trying to do is, at this moment, we're trying to calibrate at which pixel location what data point should be there. So I think I picked 10. So once I specify the values, and this 1 is basically me specifying that it's January of 1770. That's just an assumption I've made right now. If you don't have dates, you can just put the number as is. So now what you see is right after I do that, there are these 2 numbers that are changing on the right side. And instantly as I hover on this chart, these number updates. So I can tell that in 1793, the value of these stocks were 86. So it is kind of interactive already. But the next cool thing is, let's say I want to extract the data out of this blue curve. And so I can just go to this automatic mode, make a nice, the first thing I want to do is kind of tell this tool where to look for. It doesn't need to be very accurate, just give a rough idea of where it is, just so that it's not interfering with other labels or something like that. And the next thing you want to do is actually specify the color. So right now, there is some image processing going on. It tries to determine what all colors are there. So it has a little spectrum of some dominant colors in the image. This seems very close to the plot I used. If it doesn't seem close enough, you can just use the color picker and start picking colors off the charts. And once you've specified the color of the curve that you want, since this is a 200-year-old chart, you see there's a lot of variation in the color. This is just a way to kind of control that kind of variation. So by default, there is some number that I have put in based on what most cleaner plots are, like if you're pulling out of a chart. In this case, it is pretty noisy, so I would like to reduce this. So it's basically just controlling distance from that color that you had picked. So at this point, what has happened, this tool knows that these are the pixels that you're really interested in. And the next thing I just want to do is run a simple averaging window algorithm. There are a bunch of other algorithms that are available too, but if you're just using the tool first time, I would say just use default stuff and hit run. And in an instant, you see there are about 264 data points that have been picked. And I can kind of zoom in and visually inspect how good the detections were. And if something looks a little bit off, like for example, this point looks a little higher, I can always switch to the manual mode, make small adjustments. And once I'm fully satisfied, I can just I can view all my data. So these are years, months. I can make it even more precise and add some dates. And I can download this as a CSV file. Or the next thing you can do is, the coolest part about this, is just press a button. And this data will now go to Plotly. So now you've gone from a 200-year-old static image of a chart to something very interactive in just a matter of a few minutes. And if you know what you're doing, you can actually get a lot of mileage out of this, which I'm going to demonstrate as I go. By the way, there's a very detailed version of this demo on the website as well. So this tool, this is just a basic workflow of how to go about this. After you load the image and specify what type of plot it is and calibrate all your axes, it gives you two ways of really going about it. So if you have a nice, clean image, you can just pick an automated approach. You specify a region of interest, you specify your color ranges, and you pick some algorithm. It just basically extracts hundreds of points out of your data. But in some weird plots, or that's something, in cases where the automatic extraction doesn't work as well, you can just use manual mode, or you can actually keep cycling between these and keep making fine adjustments till you're completely satisfied. Of course, the ultimate test is to just visually inspect. So you have tools for zooming in and really looking at each and every individual point on how accurately it was picked up. Now, in this digitization process, the first thing that happens is the tool needs to map the pixels on the image to the data coordinates. And in the demonstration, I used a 2D XY chart, but there are actually a lot of different types of charts you can have. So in the demonstration I used, we put in 4 points. What the tool does is basically does a simple affine transformation, which is just some basic linear algebra. So it can also account for not just scaling and translation, which is what you're really doing if you have a perfectly aligned image, but it can also account for rotation and skew. If you're taking pictures with a camera, like on the slide that a lot of people I see doing today, a bunch of slides, in that case, you have actually a projection transform, and you can use a tool like GIMP and just correct your image. As long as your axes are parallel, this tool can work with it. That would be like a nice future addition to make. And this supports log scale axes, dates, any type of XY chart, really. And the next type of mapping is for bar charts. So in case of bar charts, you only have one continuous axis. And the other is just basically a bunch of discrete labels along the other axes. So the tool only asks for 2 input points, and it knows how to scale linearly, whether it is a horizontal bar chart or a vertical chart. Even your bars could be positive, negative, whatever orientation it is. After you've put in these 2 points and specify whether it's a log scale or not, it really knows how to handle that chart. Oops, sorry. In case of a histogram, you have 2 continuous axes, so it's not really different from any regular 2D XY chart. So I recommend just doing a regular XY calibration. If you're an electrical engineer, or if you're maybe a sailing enthusiast, I have had some of those users who basically trying to figure out the position of their sail with respect to their wind speed. And you end up running into a lot of polar diagrams in that case. And this tool asks for 3 input points and uses some geometry to kind of figure out where the pixels and data should be. And in this case, you just specify the center of the polar diagram and 2 arbitrary points on the plot. And based on whether it's clockwise, anti-clockwise, degrees, radian, it can pretty much work with any kind of polar diagram that you throw at it. If you're a chemical engineer or a material scientist, you've probably seen these. So if you have 3 species in any system, like 3 chemicals, for example, and you're doing some sort of data plotting, you see these kind of ternary diagrams all the time. And this tool just asks you to input 3 corners of this chart and pick some range of variables. A lot of images that people use, and you also see in scientific publications, are not actually charts, but they're actually things like microscope images or the schematic of this aircraft on the side. In this case, you really want all your features to get scaled with that one scale bar that is in that image. And maybe you're trying to extract some features out of this Apple A7 chip image, or maybe you're trying to get some wing shape out of your airplane. And in both those cases, just pick 2 points on the scale bar, and you can tell the tool how to scale those things. It is particularly useful when you're trying to do some basic measurements, and the tool has a couple of measurement options, like distance measurement or angle measurement. This is an image from National Geographic magazine, and they just published a picture of this bird with a scale bar on the side. And you can use a tool like this just to determine, what the wingspan is or what the other sizes of birds are. But you can even use this on something like Google Maps screenshot, for example. There's also an angle measurement tool. This is something you do quite a few times if you're doing surface chemistry. Of course, for this, you don't need to do any calibration. You can just start doing angle measurements. In the future, there will be some support for doing path lengths, areas, and all those things, but they're still kind of in the pipeline. After you've done all this mapping from pixels to your data points, the next thing you want to do is extract your actual data. So you want to do some color or shape-based segmentation and figure out where your curves are or where these data points are. And the other thing you want to do is find what the region of interest is. In a lot of charts, what happens is you have multiple charts in the same image, or you might have tons of labels like legends or other labels that are basically same color. They look very similar to actual data. But you want to separate all those things out of the image. And finally, once you've done that, you've identified what the pixels of interest are. That's when you want to do your thinning or centroid estimation on all these pixel clouds. Now, when you do those centroid estimations and thinnings, you really want to have something that is very sub-pixel accurate. So if you're just doing granular to integer pixels, it doesn't work very well because a lot of charts actually tend to be pretty low resolution. And what I have seen is humans are very good at the first 2 tasks here, but they are really bad at doing the last part, whereas finding where the mean point is for these pixels. So for the first 2 tasks, the tool kind of asks you for the manual input, like to specify the mask and specify the color range. But the thinning stuff, it can take care of for you. For that, there are a bunch of algorithms that are in this tool. The first one is what I just demoed a few minutes ago, and it's called the averaging window algorithm. This is just a pretty basic algorithm, and I kind of just made up a name for it because I didn't even bother looking if it's a legitimate algorithm or not. But over the years, I've kind of fine-tuned it and made it work with a lot of different curves. And there are 2 adjustable parameters on this, basically this delta x and delta y. What these are basically the size of the window that the average point is found in. So if you have a very thick curve, you just increase this delta y, and you'll guarantee that you get a single point in that thick curve. If you want very tight spacing in your x direction, just reduce the delta x value, and you will get more points in your x direction. This works great when you have continuous curves, like the one shown here, or even for a lot of data points, it works really well. But a lot of times, you don't have continuous curves, and for that, there is a different algorithm called x-step with interpolation. This has 6 adjustable parameters, but in this case, what happens is the 4 of those are just to specify the bounding box of your data that you're interested in, and the delta x step is just to kind of specify the spacing that you want all your points in. So you can control at what x values you want your y values to be extracted out of this tool. And the cool thing about this is it does a cubic spline interpolation. So it can find where the data is, even between the gaps. So if you have some discontinuous dashed lines, like the one shown in left, or if you have some noisy data, it also has a smoothing parameter, so you can kind of take some noisy data and just get the gist out of it to some extent. I don't know how many people actually use that particular piece, but I have used it a lot of times. There's also a specific algorithm just to work with bar charts and histograms. In this case, these two parameters are essentially just to make you work better with very noisy, low-grade images, like if you're working with an 80-year-old bar graph, for example. So delta y will let you give you some leeway in how sharp the edges are. The next algorithm is called a blob extraction algorithm. This is just a modified implementation of something that is, for image processing guys, you probably know of this already. It's called connected component labeling. So this is great for finding data points in an image, but it's also great at finding area and moment invariance of an individual shape. So this is like a rotational invariant where in this image, for example, all the A's and the stars that are just rotated by an angle, you can kind of separate those based on the moment invariant. So I was using it for a lot of my fluid dynamics experiments where I had different types of particles in my image and I was trying to find where they were located. But a lot of people I've seen have used this on very noisy type of data sets. WebPlotDigitizer does extraction based on color. So a lot of times when you have black and white images that have a grid like this in the background, it becomes a problem to do this kind of color-based extraction. So to counter that, there is a grid removal tool. It works very similarly to any kind of curve extraction that is in there. But, and you can kind of control if you want to remove just the horizontal lines or vertical lines. The only downside is that trying to remove these grid lines, you might lose some useful data in some places. But there's really no way around it at that point. You've kind of lost that information anyways. A common question that gets asked is, what kind of accuracy can a tool like this give you? The best way to kind of test it out is just take some known data and plot it in a few different types of images and compare the digitized values with what you get out of the tool. And in this example, this is just a quick summary just to kind of give you an idea of what happens. If you have low-resolution images, and if you have very clean charts like the bar chart, the line graph, and the point chart that is in here, the tool works great. Like most errors are actually below 0.5% in this case. But if you're doing something like the thick dashed line and you're doing interpolations and you're trying to average out on thick curves, your errors might increase. So whenever you're working with data, you have to be a little careful and figure out what your tolerances are. And my advice in this area is if you have a chart that you know that some points are definitely at certain points that you know of, like integer values like 2, 4, for example, I would use that as a reference value to get an error estimate. If you're very interested in trying to dig deep more into these kind of tools and how they scale up, there are 3 independent studies that were done. I did not fund any of these, but they did use WebPlotDigitizer and compared it with other tools. And all of them have concluded that it is an easier to use tool, it's faster, it's more accurate than anything else that is out there. Now, since it's a nice, easy-to-use tool, it's actually very simple. People have used it in various creative ways that I never thought of when I wrote this. For example, here someone's used it to just extract contour lines out of a relief map, and apparently it works well. For those who've worked in a research lab and have seen ancient equipment that can never work with any modern computer, you might be able to try these kind of things. And this is another example where someone's tried to use it for their experimental setup. So here's somebody trying to study structural properties of this piece of wood, and they put these red markers on the top edge, and they're trying to figure out what kind of deflection they get based on different loads. So they just took these different images and used WebPlotDigitizer to extract locations of all these red markers and figure out what kind of deflection they were getting. There are a few things that are sort of under development right now. I'm working on an R package. Since doing these kind of reverse engineering type things works really well with people who are doing data science, it's almost natural to have an R package for this. So right now, this package is kind of under development. All it really lets you do is launch the tool in an offline mode. But the ultimate goal is to make it super interactive with R, and so you can kind of take a PDF, take it apart, and drop it in this tool and things like that. There's also a native desktop tool I'm working on. As over time, last 2-3 years, a lot of companies who make engineering software have come up to me. They want to embed like a C++ library in their tools, or even just do a lot of batch processing with hundreds of images and maybe do a lot of different kinds of stuff. And a native application kind of lets me use things like OpenCV and TensorFlow and whatnot. One of the biggest strengths of this tool is that it's an open source tool. And if you're not a programmer or just a user, I still encourage you to go to the GitHub website. And if you have ideas, just drop them in there. Even at this point, even though this is a completely open tracker, 90% of my communication is still through emails. I would really like just having a list here. And these are a couple of useful links. That's where the website is hosted. That's the source code, and that's how you can get a hold of me. And do you have any questions?
That was awesome. Yeah, thanks for sharing that with us. I'm curious, when you're extracting multiple lines from a plot, is it easy to just, column bind them together? Are they at the same, like on the x-axis, is it the same interval?
Yes, so the GUI is not that intuitive in that area. That is something I'm still working on. But you can have a multiple data set support. So you basically in the same chart, if you know there are multiple different charts, you can add them individually as a data set. And in using the X step with interpolation, you can just control what your X points are. And that kind of makes you work. But yeah, that is a very common question, actually. It's something really high on my list.
So I think sort of related to that, how well does it handle the sort of lines in the plot crossing over each other if they're not, especially if it's like a black and white image? Are you able to sort of handle that well?
So in that case, at the intersection point, there is no curve tracing really going on. So what happens is you might want to make your mask just kind of follow the line that you're interested in, and then it works fine. And the manual tools are actually super easy to use. In case there is a small mistake, you can just go back and correct it. So that's kind of how you handle that right now.
Do you have any interest in video?
Actually, since I did a lot of video analysis in my grad school, that is on my to-do list. But doing that in a web-based tool is kind of difficult, and that's sort of why I'm working in that native direction. But yeah, that is definitely on my list, especially tracking stuff and that kind of stuff, yeah. All right, thank you, everyone.